Good morning, pre-calc. This is an introduction to parametric equations. We are going to do an exploration worksheet to try to help describe what a parametric equation is to you. And we're going to start by looking at an example. So here we go. Suppose two bugs are crawling along linear paths. Bug 1 begins a trek toward a point 70 inches from where he begins, traveling at a speed of 12 inches per hour. Bug 2 travels at a speed of 18 inches per hour, but leaves 1 hour after bug 1 from a similar starting position on a parallel path. And this is the tortoise and the hare. Here you have the tortoise. He starts off going kind of slow, and the hare starts later, but he's going fast. Who wins the race? How do you get there? And that's really the essence of a parametric equation, is you're going to introduce the idea of basically of more variables. Okay? So what we're going to do here is we're going to come up with a set of equations to try to model the paths of these bugs. Okay? And bug 1's distance. And distance for us is always equal to rate times time. So he's going 12 inches per hour times the time of t. That's bug 1. And then bug 2 is going 18 inches per hour, but leaves an hour after bug 1. So his time is t minus 1. And what we're able to do is we're able to take our calculators, and you really need one of these to do this. We're going to take our calculators, and we are going to watch the bug race. We're going to see which one wins. So I took some screenshots here, and you're going to take your calculator, and you're going to make it look like what this one looks like. So first of all, you hit the mode key right here. I'll hit mode, and we are going to change it to what is on the screen. Okay, so mode, they want normal, float, radian. It looks like we want it in radian. I'll go down there, and there is a new one. We've always had it in function before, but what we're going to is we're going to go down there, and we're going to change it into what's called parametric. Connected, sequential. I'll go under simultaneous. Thank you. No, thank you. I'll go under simultaneous. I'll hit enter, and then real and full. So I have everything up there. And when I hit my Y1 key, something interesting is going to happen. It's not going to be Y1 anymore. I have a stat plot on here. I'm going to go up and I'm going to clear that out. Oops, Y1. I'm going to go up and I'm going to hit enter on that to turn that stat plot off. But I'm going to clear out these equations. These were some parametric equations that I've used in the past for a different problem. We'll probably see those again. But we're going to watch the bug. So bug 1, its x value was in 12t. So I'm going to enter 12t for bug 1. And notice when I hit the xt theta n button right there, it actually comes up with 12t. And t is really a variable for time that tells us how far he is and at what point. And then this y value of 3 basically means we're going to put him in lane 3. I'm going to put this bug in lane 3. And then the other bug was going 18 times t minus 1. So I'll put t minus 1. And that, t minus 1. And that bug was in lane 1. So we put one bug, the slower bug is in lane 3 going at 12. The other bug was in lane 1 going at 18, but left an hour sooner. Okay, and we have all of those entered. Okay, let's keep looking. So now my window, I'm going to set up the time. So I hit my window key. My time minimum 0. My time maximum I want to be 6. That'll track the bugs over 6 hours, because the scale is in hours. I'm going to step my scale by point. It looks like it wants me to go by 0.01. My x minimum it has at 0, x max at 70, x scale at 10. It wants a t-step. We already have that. We already have that. We already have that. It wants a y-min of 0, 4, and 1, these last ones. Y-min of 0, y-max of 4, and a y-scale of 1. And if I hit graph, when you hit graph, it's going to pop up on your calculator. It's going to show you the bugs racing. Oh, there goes bug 1. He left early. Oh, here comes bug 2. Oh no, bug 2 is going to win. He overtook bug 1 and did the 70 inch meter, whatever the scale was, race.
and got it. So really, maybe I can quit out there. I want to try to show you that again. I think it'll actually pop up to the graph. Oh, nope, it already popped up to the graph. You'd have to go back in and enter something different for it to regraph it. But when you do it, if you have them graph simultaneously, it'll graph those two at the same time. So let's look at this. Why is there no t variable in the y equation for each bug? And I would say that was because the y equation, well, that was the lane that we put them in. That was the lane assignment. Graph the bugs in motions. Who won? We saw bug 2 win. Bug 2 left later, but was able to overtake bug 1. And at what time are the bugs the same distance from their starting paths along, from their starting points along the paths? Also, where are they? And I'm going to do this from an algebraic standpoint. One of the equations was 12t. That was bug 1. And bug 2's equation was 18t minus 1. And it says, at what time were they the same distance? And that really is the answer to the question, when does 12t equal 18t minus 1? When are those two equations equal? So I can distribute. I get 18t minus 18 equals 12t. Minus the 18 over, I get negative 6t equals negative 18. And if I divide, I get a t-value of 3. A t-value at a time of 3 hours. I think it was in hours. Bug 1 overtakes bug 2. And it also asks, where were they? Well, bug 1 was 12 times 3, or 36. I'm going to put units. I think it was inches. I'm hoping this one is 36, because that's when they would have been the same. So I'll do 18 times 3 minus 1, which is 18 times 2, or 36 units. And if it was inches, it would be inches. At a time of 3 hours and at a distance of 36, bug 2 overtakes bug 1 and takes the lead. And that really is the essence of a parametric equation. So I'm going to show you a little bit more here about parametrics. That's a parametric. Not only the where, like where is it, like how far out and how far up, your x and your y value, but a parametric equation also talks about the when value. Parametric, whenever you introduce that idea, what is a parametric equation? It is the idea that there's a time element that exists within the equations. So not only, hey, where does something happen, but when does it happen? And if you can remember that, parametrics are pretty easy. For example, you travel towards Fremont directly northwest at a rate of 75 miles per hour. The origin of your trip is Concordia. How far west and how far north are you in 30 minutes? This is the parametric equation. You could tell if Concordia was your starting point and you went at that northwest value. You can almost do like a Pythagorean theorem or a trig problem where you figure out how far out one direction, how far up direction are you out at a specific time. Can anyone figure this problem out? I mean, we could go through that, but here's a couple other example problems. Dropping a water balloon on a roller coaster from a helicopter. Now, you couldn't just drop it at any point. You'd want to see that roller coaster coming, and you want to drop it so that roller coaster and that water balloon, they hit at the same time. One that I remember whenever I do this is a little ornery back in grade school, and I used to like to chuck snowballs at cars when they'd go by and then take off running. We had this specific spot where we'd do this. So you had to, like when the car was coming, you had to lob the snowball up so they got to the same point at the same time. A quarterback leading a receiver. You want the ball at the right spot at the right time. Missile hitting a moving plane. Torpedo hits a ship. That's definitely parametric. Hunting and trap shooting. Those of you that are on the trap team, the little clay pigeon comes and you want that shot to hit there at the same time. If it's too early or too late, you miss the clay target. Hey, dodgeball. Dodgeball's a parametric equation. Get the arc of that ball at the right point when the person is moving and you try to hit them. All these are examples of parametric equations. Okay? Let's go ahead and let's look at a second parametric equation, sheet 2. We're going to consider another bug, only this bug is going to go on a trigonometric graph path. And
You'll be surprised how crazy this path of this looks like. So let's go ahead and let's set up our calculator here. We're going to go back to our y equals, and we're going to change quite a bit here. So let's clear off what we got. And I hope you do this. This is pretty cool. I'll ask you to do a couple things at the end of this problem that are pretty cool. So just stay with me. So let's type in. Oh, I gotta have my mode. It has to be okay. My mode is in radians, so I'm good. Back to my y equals. I want 4 cosine of t. Close off that parentheses. Plus 5 cosine of 3t. So there's one bug, it looks like. And then my y value is going to be sine of 3t, sine of 3t plus t. Okay, so there's the bug's path. And we're not really racing bugs on this one. We're just going to try to figure out where a bug is and when he's at a specific spot. So that's kind of our deal here. So we got that. So let's set up our window now. I think this path, it's going to last a little bit longer. So I'm gonna go from 0 to 12. From 0 to 12, and I'm still going to step it by 0.001. So this is going to track every 100th of a second where this bug is. And we'll track it at different rates here in a second. So my t step is, okay, so my x minimum, let's go x minimum, go negative 30 to 30, I think was the scale that I wanted on. We might come back and change that one. And our x scale, let's just go by 1. And our y minimum, let's go from 0, and our y maximum, let's go to 30. I'm not sure if that enters it. Let's see what happens when I hit my graph button with that. Negative 30 to 30 for x min, x scale 1, y min 0, y max 30, y scale 1, and I'm going to graph it. And there's my bug. He is traveling. Oops, I'm gonna change the scale here in a little bit here, but got this bug and he's running around almost like this little curlicue pigtail path on my graph. So there he is. He's like a little fly. You know, he's just bopping around, just doing his thing, and it's gonna trace the path of that fly over the 12 seconds that we told our graphing calculator to trace it. So it looks like my scale is a little bit bigger than I need to, so sometimes you'll actually lock your calculator up. You can see it thinking here. If you have it go too slow, if you change your, I always have somebody do this and they have to end up taking their batteries out of their calculator. Change your t-step, so how often it reads it, to like 0.0001. It'll show you every thousandth of a second, and it'll basically lock your calculator up. So there it is. I'm going to go back to my window, though. And I'm going to change this from, I'm going to go negative 15 to 15. Let's try that. And I'm going to speed it up. So my t-step, instead of being 0.01, I'm going to make it 0.10. So now it's only, instead of every 100th of a second, it's going to tell me where he's at every 10th of a second. And I think 15 should cover it. Now watch the difference here. This is crazy. Watch how much faster it goes. There's the bug every 10th of a second. And you can see how much faster it is. That's a pretty darn good graph of that bug's path. But the reason it went so much faster is rather than 0.01 telling the calculator, hey, graph him every 100th of a second, we graphed it at 0.1, which is every 10th of a second. Let's see what happens when we graph him every 1 second. So let's just change my graph to 1 second. So 0 to 12 with 1 second t-step, and I'll hit my graph button. And it's not a smooth curve at all. He was here at 0, here at 1, here at 2, 3, 4, 5, 6, 7, 8, 9, 10. I mean, that graph isn't smooth because it's only graphing every second. So I really liked the t-step at 0.1 on this graph. And you might have to play around with these t-steps according to whatever it is. So I'm at the graph again, and there it is. And I think we can do everything that we need to do now with this. It says, so number 1, it says, where does the bug start? Well, the bug starts at a time of 0. So I'm going to trace, and it will say t0. I can plug in 0. I can hit enter. And the bug starts at the ordered pair 9, 0. So I'm going to write that in. Where does the bug start? The bug starts at the point 9, 0. Where's the bug 1 second after starting? Well, again, what we can do when we have our calculators, and you will do these on a calculator, you'll see how this works. But if I trace 1, it'll tell me the bug was at negative 2.78, 1.14. Negative 2.78, negative 2.78, and 1.14. And it says build a table for the bug's location. And what I would like to do is simply hit my table button. And you can see I'm not going to go ahead and fill all these in. What I want you to understand is if you wanted actual values at each second, here they are. I can go and I can look at the different positions of the bug. Like the last second, the bug that we actually measured, the 12th second, he was at the point 2.73, 11.08. And we can find the bug's location at any time. And we could go over here and we could set our table set. I mean, I started my table at 7. I could start my table at 0.1. I could find him every 10th of a second. There's a lot I can do with this. So build a table for bugs times. I'm just going to put here table setting on my TI will do this. Table setting on my TI will actually figure out what that is. Okay, number 4, use a table of values to graph the bug. Okay, I'm just going to go ahead and here's the bug's path. Bang, I got the bug's path, and we can look at that on our graphic calculator and we can see, again, the bug's path. That's not a perfect picture of it, but if you have your calculator, you can see it actually looks very symmetrical. I bet that would all come up there and it'd be a very symmetrical graph the way it is. How should we adjust the graph settings if we want to see the bug's path in slow motion? Okay, well, what we would do is change the time setting to a smaller t-step. In fact, if you wanted to see it in really slow motion, you could change the t-step to 0.001. Okay? And we graphed it around the coordinate plane already. Consider a bug's nonlinear path as it runs around the coordinate plane. And how does the graph of at every 100th of a second compare to the graph at every 10th of a second? Well, the 100th of a second is a very fine graph. It shows me more accuracy, if you will. The 10th of a second, it speeds it up and it shows me the same path, but it only shows it to me every 10th of a second. So how does the bug's path at every 100th of a second? 100th of a second is very accurate. Okay, and I think we only have one more. That might have been it. Let me see. We got one more to do. And we got one more. And let's watch this. We're going to graph bug A. Oops. We'll graph bug A, bug B, and bug C on the same coordinate graph. And we'll watch one more bug race here. So I got Y equals, this one's easy to plug in. I'm going to go with 8 cosine of T. Okay, and then my Y value is 5 sine of T. And delete that and that. 8 cosine T, 5 sine T. That's bug A. Bug B is 3T and 5T. 3T and 5T. And then bug C here is at 3T and 4T. 3T and 4T. And I don't think I need 12 seconds here, so I'm going to go ahead and set my window up. I'm going to set my window from 0. Let's go from 0 to 7. I think we'll handle it. We'll t-step it by 0.1. And I think this one, graph it on the picture below. This one is in the first quadrant. So when I set my x-min and my x-max up, I'm going to set my x-min at 0. And my x-max, let's stay with 15, x scale 1, y-min 0, y-max 15, y scale 1. Let's graph them. Okay.
Cool. So we had this happen. We had a graph come like this, and then we had one come up like this, and we had one come up like this. Now, if you think about this, one is 3/5 t and one is 3/4 t. Up 3 over 4. Bug A, bug B was 3, and a rise of 5, a run of 3. This one is a rise of 4, a run of 3. So this one right here would be bug B, and this one would be bug C. And this circular one over here, this must have been bug A. Bug A. So there was A, B, and C. And it says, do bugs A and B collide?
If they were at the same place and the same time they did,
I'm going to have to go check that. Do bugs B and C collide? Do bugs A and C collide? Oh, man. So they're asking me for collisions. They're asking me, did we get bug splat? Well, the way you can test that is you can slow it down. So I'm going to go to my window. And rather than having a t-step of 0.1, I'm going to go a t-step of 0.01. And I'm going to enter it, I'm going to graph it, and I'm going to see if I have bug splat. So there's one bug, and there's, splat! That bug right there and this bug right here, they splatted. This one got out of the way, so we did not have bug splat. So it looks like to me, bug A and C went splat right here, but bug B scooted by. So do bugs A and B collide? No, I don't think A and B did not collide. No, they're at different places at different times. Do bugs B and C collide? B and C, no, they're definitely going different directions. But do bugs A and C collide? Yes, they did. They appeared to collide and be in the same place at the same time. That is an introduction to parametric equations. As we go through this, we are going to enter the time element into doing this stuff and see if we can come up with some really great problems to do. All right, have a great day.